also know that computers don't read words, at least the same way we do. Computers only read numbers. To a computer, the word love is 108, 111, 118, and 101. These are the ASCII codes for each letter. That's it. No warmth, no weight, no memory attached. Just four numbers that happen to represent four letters. Now think about the word grief. What do you feel when you read it? A computer just sees five numbers. The numbers are there. Everything that makes grief what it is completely absent. Now, imagine trying to explain spicy to someone using only a ruler. You can measure the length of a chili pepper or its width. You can even assign it a heat unit number. But none of those measurements capture the burning sensation on your tongue. And converting language to numbers had the same problem. The numbers existed, the meaning didn't transfer. And before machines could actually do anything useful with language, someone had to solve this. How do you make numbers carry meaning? The first step was figuring out what the machine actually reads. And it's not words, it's tokens. A token is the basic unit the model works with, and it's not always a whole word. The common word, unbelievable, might become three tokens: un, believe, and able. A common word like the is one token. A character like exclamation mark is its own token. Now, why? Because you can build a vocabulary that covers every possible word in every possible language, including made up words, brand names, slang, and words that haven't been invented yet. So, instead, you build a vocabulary about 50,000 words to 100,000 pieces, and any word in any language can be assembled from those pieces. The transformers changed everything. Look at what happens to it. Transformer becomes transform and two tokens. Each token gets a number. It's essentially its ID in the vocabulary. That's what the model actually receives, not the words. It just receives the numbers. For example, take the word ChatGPT. It breaks into chat, G, and PT because ChatGPT didn't exist when the vocabulary was built. So the system handles it anyway by decomposing it into pieces it knows. Now think about how sheet music works. A composer doesn't invent a new symbol for every sound that's ever been made. They use a fixed set of notes and combine them into anything. Tokens are the same idea, a finite set of pieces that can represent infinite text. And the meaning of those tokens, that's the next step. So we have tokens now, essentially numbers. But numbers don't have any meaning. How do we fix that? The answer is embeddings. And this is genuinely one of the most beautiful ideas in this whole story. An embedding takes a token and converts it into a location, a point in vast mathematical space, a space with thousands of dimensions that we can't visualize but we can reason about. And what makes it remarkable is what the space looks like. Happy and joyful end up almost in the same spot. King, queen land close together. Coffee and engine are far apart. The model has no idea what any of these words mean. It's never tasted coffee, it's never met a king, but it knows where they live relative to everything else, and that turns out to be enough. Look at this map. Three clusters. Up in one corner, we have king, queen, prince, and princess. Over in another, we have coffee, tea, espresso, and latte. And in third area, sad, unhappy, grief, and melancholy. Nobody programmed this. Nobody said, put royalty words in this corner. The model saw these words appearing in similar context billions of times and they migrated towards each other. Now, look at the word sitting between the hot drinks cluster and the negative emotions cluster. The word bitter. It can be bitter coffee or it can be bitter disappointment. Both are valid. And the word genuinely lives between two semantic neighborhoods, and the map shows that. Location is a proxy for meaning. The address of a word tells the model what kind of the word it is. So, how do embeddings learn? We know that not through definitions. They learn meaning through exposure. The model sees the word coffee appearing near morning, cup, drink, hot, caffeine, and this happens billions of times. So gradually, the coffee point in space gets pulled toward those words. It migrates to a neighborhood where its conceptual neighbors already live. Nobody told the model that doctor and hospital are related. It figured that out because they kept appearing in the same sentences. Think about how you learn the word sophisticated. Not from a dictionary, right? From hearing it in certain kinds of conversations, around certain kinds of people, or in certain context. You built up a feeling for the word through exposure and not definition. And that's exactly what embeddings do. Through the company, a word keeps, not through a formal definition. The difference? Your exposure involved actually being in those rooms, around those people, whereas the model's exposure is purely textual. No rooms, no people, and no experience. Just the statistical co-occurrence of words across trillions of sentences. And yet, the result is extraordinarily rich. So, we solved rule writing. Neural networks could learn from examples, but there was a problem, a significant one. These networks read words in sequence, one at a time, left to right. And as they moved forward through a sentence, the earlier words faded. Look at this sentence. The trophy wouldn't fit in the suitcase because it was too large. And by the time the network reads the word it, the word that needs to be resolved, the word trophy was already fading from its memory. Suitcase was dimmer, and the context that would let it answer which one was too large was slipping away. For short sentences, it's fine, but for anything longer, like a paragraph, a legal document, a conversation, the network was effectively reading with amnesia. Each new word slightly erases the one before. And this was another barrier, and it's what made the next breakthrough so important.